welcome to our Quantum Deep Dive. Today, we're exploring a really fascinating essay by Jörg Oeschnepat that sits right at the intersection of data science and physics. At its heart, our challenge is pretty simple, right? How do we find meaningful groups in what just looks like a chaotic sea of data? Okay, so let's dive into this. We're going to start with the problem itself, explore the limits of our current tools, and then take a leap into the quantum world to see how it offers a new solution, its real-world impact, and, what the future holds. First, let's just make sure we're on the same page with what we mean by clustering. It's a core task in machine learning where we're trying to find hidden structures without any pre-existing labels to guide us.
And you can do this in two main ways. You've got hard clustering, where each data point belongs to exactly one group, or soft clustering, which allows for overlaps and probabilities. It's a bit more flexible.
For decades, we've relied on these classic algorithms like k-means, which tries to minimize the distance of points to a cluster center. And they work beautifully for simple, really well-separated data. But what happens when the data gets complicated? Now, what's really interesting about this slide is it shows that breaking point. On the left, a simple task. On the right, a really complex one where methods like k-means just completely fail. And this brings us to the real villain of our story. It's called the curse of dimensionality. In simple terms, when you have way too much information for each data point, everything starts to look equally far apart, and our classical tools basically go blind. So, how do we get past this wall? Well, it's by changing the way we see data itself. Instead of thinking about classical bits, a 0 or a 1, quantum computing uses qubits. Right, and the crucial point here is the principle of superposition. A qubit can exist in multiple states at once, which lets us encode and process information in a fundamentally more powerful way. This lets us move from thinking of data as just a collection of separate points, like this, a simple scatter plot, to thinking of it like this, a continuous wave function, where the peaks represent the areas of high data density. And this is really the heart of quantum clustering. It uses the mathematics of quantum mechanics, specifically the Schrödinger equation, to translate that data wave into a 3D potential landscape. And this illustrates the process brilliantly. We build the wave from the data's density, use physics to generate a landscape, and the clusters just reveal themselves as the deepest valleys. The algorithm literally involves letting each data point roll downhill into its nearest valley. So let's compare them directly. Classical methods, they kind of impose a geometric structure on the data. Quantum clustering, on the other hand, lets the structure emerge from a physical-like process. It's a totally fundamental shift in approach. Now, this isn't just some theoretical exercise. Let's move on and see how this builds into real-world applications. In medicine, it can help find these really rare disease subtypes that are just totally missed by other methods. Or it can identify stable molecular structures, which could seriously accelerate drug discovery. And in finance, it can spot these subtle market patterns and group investments by risk in ways that simple linear models just can't, giving you a much more robust view of a portfolio. And in material science, it can help us navigate these incredibly complex energy landscapes to discover the right configurations for next-generation materials. Okay, this all sounds pretty incredible, right? But it's really important to ground ourselves in the reality of today's technology. We are currently in what's known as the NISQ era. And what that means is that today's quantum computers are powerful, for sure, but they're also noisy and error-prone. So the most practical path forward right now is a hybrid one. So the key here is that we combine the strengths of both worlds. We use classical machines for all the heavy lifting, and then we call on the quantum processor for those very specific, very complex calculations where it really has an advantage. So what should you really take away from all this? It's that quantum clustering isn't just a faster algorithm. It's a fundamentally new lens for finding patterns. It transforms noise into meaning by treating data as a physical system. Which leaves us with a final, kind of provocative thought. We really want to thank Jörg Oeschnepat for the incredible essay that formed the basis for this deep dive. For much deeper exploration of these topics, please visit his website at schnepat.de. Thank you for joining us, and goodbye.
Schnepat.de is a private project by Jörg Oeschnepat dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.